Hello everyone. Today I'm going to be going over another principle of trigonometric functions. After this point in the series, we're going to be venturing more into how to solve not geometric problems, but problems they give you where you have to solve for a value of theta given a certain equation of trigonometric functions is true. For example, an equation would look something like cosine squared theta plus sine theta minus 1 equals 0. This is the kind of equation they'd expect you to solve, and you're going to be using properties of cosine and sine, like I will teach you in the next few videos, to solve this kind of equations, and these equations are normally going to be for a given interval of theta. And I will explain this in more detail in my final two videos, which will be generally just summarizing all of my tips and tricks for these kinds of questions. But in the next few videos, I'm going to be going over the theory behind most of these formulae. For example, how we can get the sine of an angle plus another angle, and the same for the cosine and tangent. And also, what I especially want to talk about today is the theorem that sine squared theta plus cosine squared theta is equal to 1. Now, this theorem exists because of the nature of a right angle triangle and like the Pythagorean theorem. So, say you have some arbitrary right angle triangle here, and you have the hypotenuse to be A, and say this angle here is going to be our theta. Well, first you know that this side here, or rather I'll just make sure to label this as the right angle. This side here is going to be A times sine theta, because sine theta will be, let's call this B, and let's call this C. Sine theta is going to be the opposite side, B, over the hypotenuse, A. And therefore, B is equal to A sine theta. And the same kind of principle applies when we're looking to find the side length C. So we know that cosine is the adjacent side, C, over the hypotenuse, A. So since cosine theta is going to be C over A, C must be A cos theta. Well, A cos theta. And now we know that A is equal to, or rather, we have a right angle triangle where the hypotenuse is A and one angle is labeled theta. The two sides are going to be A cos theta and A sine theta. And now what are the implications of this? So we know from the Pythagorean theorem that the sum of squares of two legs of a right angle triangle, legs meaning these shorter sides, not the hypotenuse, the sum of the squares of the lengths of the two legs of a right angle triangle is going to be equal to the square of the hypotenuse of that same right angle triangle. So, and this is expressed algebraically in the form a squared plus b squared equals c squared. So what happens when we apply it to this triangle that we have here? For any given a sine theta squared plus a cos theta squared, we're going to get a squared. And you know this from the fact that a sine theta squared is going to be a squared sine squared theta. This can also be written as sine theta squared, but in these next few videos, I want you to get more used to using this notation where the exponent goes after the name of the function rather than the actual theta. So you have a squared sine squared theta, and then plus a squared cosine squared theta is equal to a squared. And now what you can do here is just divide both sides by a squared to find our original identity. So we're dividing by a squared here, and we get that sine squared theta plus cosine squared theta is equal to 1, or because a squared over a squared is 1. And we have our identity here. And you can also figure this identity out directly from any triangle on the unit circle, because for any triangle on the unit circle, we know that the vertical is going to be the sine theta, we know that the horizontal is going to be the cosine theta, and we know that the radius of the unit circle, given that it's a unit circle, is always going to be 1. And with the Pythagorean theorem, we can infer directly from this that cosine squared theta plus sine squared theta must be equal to 1. Now, what are the applications of this? Well, say you have an equation like this, where you are in the know that cosine squared theta plus sine theta minus 1 equals 0. You can rearrange the identity that we just discovered, sine squared theta plus cosine squared theta equals 1. You can rearrange this to find that cosine squared theta is equal to 1 minus sine squared theta, and that sine squared theta is equal to 1 minus cosine squared theta, and so on and so forth. So these two identities are going to be very helpful when you want to switch stuff around in quadratic equations, because you have a square term here and a linear term here, just with an exponent 1 and then a constant. And this looks like a quadratic that could be solved. You're just solving to find the value of sine theta. So you take the identity that 1 minus sine squared theta is equal to cosine squared theta, because you're switching this into this, and you get 1 minus sine squared theta plus sine theta minus 1 equals 0, or that minus sine squared theta plus sine theta is equal to 0. Or if you want to factorize out the sine theta, you'll get that sine theta 1 minus sine theta is equal to 0. And say when sine theta is 0, you get theta is equal to like 0, 180, 360, and so on. And when this expression is equal to 0, sine theta is positive 1, and so theta could be also 90, 270, 450, and so on. And that's basically the application here to solving these kinds of algebra questions that use trigonometric functions. And we're going to be going over more of this in the future videos. Alright, so thank you for watching.